kind of keep up with this idea that population density is talking about a certain population over an area right here. And example 2 is going to be a little bit tougher, so let's see if we can't work our way through this. Example 2, we're going to be using the formula or a formula for population density right here. So let's take a look at what's going on here. How about a volunteer to read this for me first? Thanks, Jaden.
A circular region has a population of about 21,400 people and the population density of about 425 people per square mile. Find the radius of the region.
Okay, so what are we asked to find right here?
Radius.
A radius. So if we're asked to find a radius right here, the assumption is we're looking at a region that's what shape?
Circle.
Circle. So I'm going to make a picture here real quickly, okay? I'll do my best to draw a circle. Don't make fun of my art. I'm not very artistic, okay? Nobody make fun of my art. Here's my circle. Not too bad. Pretty good. I've been practicing my circles all summer long, Cheyenne. Did I do a good job?
Yeah.
Awesome. All right. It's fun. All right, and we need to find the radius of this city. Okay. We don't know what that is. All right. What information do we know up here in this problem, kids? I obviously have said we're looking at a circular region. What other information do we know? Population's how much?
21,400.
Okay, very good, Maddie. Population's 21,400. What else do we know?
Population density is 425.
The density is 425. Okay. Anybody have a thought or an idea how I might start this to figure out what the radius of this region is? How about if I back up? How did we define population density yesterday?
The amount divided by amount of people per area.
So I'm going to write this down real quickly. I'm going to go back to the basics and talk about what we discovered yesterday. We said, you know what, kids? Density in terms of population is equal to your total population divided by an area. Would you agree with that? Okay. Let me ask some questions. If that's kind of like a formula for population density, and you said, hey, we know this, and we know this right here, are there places to plug those values in that formula that we discovered yesterday? How about that first value, 21,400? What is that 21,400 representative of? Population. So right up here by population, what value could I fill in?
There's a white Nissan Altima right outside the office with its lights on. White Nissan Altima right outside the office with lights on.
All right, Keegan. At least they caught you. That would be a bad day in the rain if your battery was dead, right?
Are you wanting us to write this down?
Absolutely.
Okay, I wasn't sure.
Yep, anytime I write down up there, you should be writing this stuff down. Okay, so what can I plug in for population? What value, kids?
21,400.
All right, so this is going to equal 21,400 for my population. I'm going to plug it in up there. Let's see, I've got another value up here, 425. That 425 is a what? It's a density, isn't it? So what can I plug in for density right here, kids? Thank you, bud.
425.
425. Okay. So my question becomes, kids, and this is how I want you to start thinking about these types of problems. What values do we not have here within this formula up here? We have the density, we have the population, but we don't know the area. Now this is critical right here, and hear what I say. Since we're talking about finding population density relative to a certain shape or area, we've got to consider the shape we're working with. In that problem up there, what kind of shape are they asking us to talk about or describe in this situation? Circle. So this is where you're going to have to recall some things. And if you're not sure or you don't remember what an area formula is, look in your Chromebooks. Okay? What type of shape are we dealing with again? Circle. So I want to come up with an area formula for my circle. Let me recall the area formula for a circle. Pi r squared, very good. So I'm going to call this 3.14 r squared. Gosh, what are we asked to find in this problem again?
Area. No, radius.
Well, we'll have to find the area a little bit, but they want you to find the radius right here. Isn't it awesome that when we put this formula in for the area that we don't know, that all of a sudden that magical r shows up, and that's going to allow you to solve for radius? Pretty cool, huh? Okay. This is exciting stuff. Watch what I do here. I'm going to put this 425 over what? To keep it the same. 1. You guys agree I've formed a proportion here? One ratio equal to another ratio here? Proportions, you can always do what? Cross multiply now, right? Let's do that. Okay. Anybody have a calculator handy? Or a phone with a calculator in it? I need you to take 425 times 3.14 first cross product. Did you get it, Keeg?
There's a different way you sound.
1,419.
1,419.2?
2.8.
Okay, either I'll go 2.8. What the heck? So read that number to me one more time again.
1,419.
What were we supposed to do?
Okay, so this is a proportion right here. Cross products and proportions are going to be equal. Okay, so the 425 times 3.14 is
I
that?
don't get that.
Well, here.
I could have done it wrong.
Oh, you're talking about the number, right?
Oh, I did 452. That was my bad.
All right, so I
It's
need to
four-
back up.
It's 1,334.5.
1,000.
Yeah, 1,334.5.
Okay, are you getting that again now? Are we in agreement? All right, Annika, thanks for the say there. Run that by me again.
Well, I wasn't sure if I
1,000.
was wrong.
1,000.
334.5.
Jaden, you agree now?
Yeah.
Okay. What else has to go with that value?
R squared.
R squared, you bet. This is going to equal then my other cross product, 21,400. Kids, are we in a situation right now where what we've set up, given a circular region, and understanding that density is population divided by area, are we in a situation where we can work this equation to figure out what our radius is now? What steps are going to be necessary to solve now? Yupper. Divide both sides by. And I'm going to do that up here, 1,334.5 up here. You know what? I'm even going to get a calculator out. I want to play the game. You guys don't just get to have all the fun. All right, so I'm taking 21,400 and I'm dividing by what again? And I come up with about 16.03. So that means that r squared is going to be what value here, kids? Careful on that.
After you divide.
Watch this real quickly. Let me make a little room up here. Okay, so from that step right here, these are going to cancel. I'll have r squared's about 16.03. Kids, to get r alone, what's the inverse operation of squaring? Square root. So we're going to take the square root of about 16.03. So I'm going to pull my calculator up here, and I'm going to hit the square root of my value here. Oh, I'm just going to put in. Well, what does it get when I hit the square root of that? 4 point what? 4.00. So the radius is really close to how many miles here?
4.
4 miles there. Okay. Okay. First thing I considered there was the
Circular region.
so the shape. Okay. We understand right here that density is population over area. So we kind of started with this formula. We plugged in what we knew. We knew the density was 425. We knew that the population was 21,400. Why did I choose to put pi r squared down here for area?
Because it's the area of the circle.
the area formula for a circle. We didn't know the area, so if you don't know an area, you have to put an area formula in there and then work through it that way, okay? How do you feel about that example? Are you with me on this? I know it's early in the morning, a lot of you are pretty quiet in the morning, but I want to make sure that you understand. Any questions about that example? Okay, that's pretty upper level stuff right there. So let's see if we can't challenge ourselves even more here. Take a look at this next one. Example 3. Okay, this is a toughie, all right? It says using an area formula. I'm telling you, this problem is what type of a problem?
Challenge.
Okay, I want you to understand you're going to use decimals to help you out. So if you want to get into your Chromebook and look at decimals, great. Get used to working that. I'm going to have it up there as well. But you know what? Let's see if we can't work our way through this, figure out what the heck is going on. Example 3, using an area formula. Let's challenge ourselves a little bit. Volunteer to read that for me, please. Go ahead, Maddie.
You are opening a doggy daycare. The outside of the play area is to have an area of 800 square yards and will be fenced on 3 sides. The wall of the indoor facility will form the 4th side. What is the minimum amount of the fencing used to enclose the outside play area?
All right, doggy daycare. Doesn't that sound like a dream job right there? All these little puppies running around. No? All right, I can tell it's early. I'll get to the point. We're going to make an assumption here. We have this building right here. Go ahead and draw this here, okay? I'm going to draw this as best I can. We have a building that's right here. This is where our building's going to be. Okay, and it says the outside of the play area is to have an area of 800 square yards fenced on 3 sides, okay? Now, this is kind of a tough one, but we're going to have to make some assumptions about this problem, all right? I'm going to make an assumption that they're going to use 3 sides of fencing right here to form a... Ooh, that's kind of bad. Okay, there's the play area. We're going to assume that the play area that the puppies are in, or the doggies are in, whatever you want to call them, we're going to assume that that area is what shape? Could be a square or a rectangle, okay? I'm going to go rectangle right here, all right? What I'm going to tell you then is this, guys. We're going to call this distance right here x. We're going to call this distance y. We don't know what the distances are. If this is x right here, and we're going to make an assumption, and I should say this up here, we're going to assume a rectangle. All right? If this is x right here, what's that make this over here, kids? Okay. What's in blue represents fencing. Okay, we're going to use 3 sides of blue fencing, and we're going to go ahead and put that up adjacent to the building to enclose an area for all these puppies that are inside there. All right? So, here's what we're trying to do, kids. The first thing that they tell you is the outside of the play area is to have an area of what? 800 square yards. So if I would take this part right in here, this area, this rectangle, how many square yards is this going to be? All right, so here's the deal. My area right here, kids, is going to be 800 square yards. They tell you that. All agree? Okay, now, what we're trying to accomplish here is this. Once we've formed this fence, they want to say, how can I get 800 square yards of area in here, but use the least amount of fence? In other words, what dimensions would I have to have here for x and for y to minimize the amount of fencing? I want to put this in there so that we're keeping our costs as low as possible, right? I mean, I could buy the amount of fence. I could make any rectangle that makes 800 square yards. But I want to make one so that we're using the least amount of fencing possible. Because using the least amount of fencing possible means what? Less money for us, okay? Here's how this works, all right? This is a tough problem. A couple things we're going to have to set up. We're going to have to set up a couple of parameters. Here's the first thing I want you to do. If the area is 800 square yards, what equation could I write involving x and y relative to 800? What's the area formula for a rectangle? Base times height, or length times width. Would you all agree with that? Okay. Would you guys agree that then the length times the width, or x times y, would have to equal what value? 800, okay? So watch this right here. We know that x times y has to equal 800. That's based off of an area, okay? The way we've set this up, that talks about my area relative to the diagram that I have. I know that that length y and that width x have to multiply to 800. Do you agree with that, number one? Give me some sort of sign you're luck right now. Okay, all agreed? Okay. Secondly, this is the part that's difficult. We want to find a minimum amount of what? Fencing. Okay. The amount of fencing we use is not considering area. We're trying to figure out the distance from here all the way to here. I want to figure out the minimum distance all the way around there. So when I'm trying to figure the minimum distance all the way around something, are we talking about area anymore, or are we talking about something else? Talking about perimeter. We're looking to minimize perimeter. Okay, pay careful attention to this because this is a really upper level concept for kids. How many of you guys down the road plan on taking calculus? These types of problems will show up all the time. Calculus is very simple once you're able to write your equations for what's going on, or once you're able to model the problem with equations. Once you have your equations set up, it's very simple. What are we trying to minimize here again? Amount of fencing, which you said was the perimeter. I'm going to call this perimeter P. That's what we're trying to minimize. And I'm going to put a little bit of a word down here as a subscript. I'm going to call it, this is what we're trying to minimize. We're trying to minimize the perimeter, or the distance of fencing that we need to use. What would an equation be, or an expression be, for the perimeter of this? How many x's do you have to add up? Okay. Do you guys agree that an expression for the perimeter would be these 2x's plus what else? Okay. So the perimeter is going to be 2x plus y. Okay. If you don't hear anything this whole class period, at least hear this. For my perimeter right here that I've written an expression for, how many variables does it depend on? 2 of them. It depends on an x and it depends on a y. Now I'm going to tell you right now, the only way that you can make stuff work is to write equations that you're either trying to minimize or maximize relative to just one variable. In other words, instead of having an x and a y over here, 2 variables, boy, it would sure be great if both of these variables were just an x, or just a y. Let me show you how this works. Okay. How many equations did I write to start this, to find a minimum or a maximum? 2 of them. Okay, here's what you do. All right. For the equation that you're not trying to optimize, in other words, minimize or maximize, go to the original one that you formed right up here. And in this case, I'm going to take a look at this one. Okay. I'm going to take a look at this one. Guys, is it possible to get y alone in this right here? What would I have to do to both sides to get y alone? Divide by x. Would you agree that if I divide both sides by x in this, y would equal 800 divided by what? Watch what happens here. Okay. From this right here, I'm going to say, you know what? Y is equal to 800 over x. Okay. Now, why would I do that? Get one variable alone up there. Why would I do that? Well, here's why. We said in any function down here that you're trying to minimize, it would sure be great if that function you're trying to minimize or maximize in some cases would be dependent upon just one variable. Okay? Kids, take a look here. What's y equal to? 800 over x. Down here, what could I replace this y with now? 800 divided by x. Okay? Let's rewrite this minimum function here. I'm going to rewrite this minimum function, the perimeter that we're trying to find the minimum amount of fencing for, which I'll call P min. All right? That's equal to 2x plus 800 over x. help me out now. That perimeter function that we're trying to minimize, how many variables is that perimeter function dependent on now? Just one. It's just an x. And you know what's really cool about this? Once you've established that, the problem becomes very simple. That part's the challenge part that we wrote up top. Do you follow me through that so far? Okay, now the second part here we said, oh, by the way, something else might help us. What did we put up there at the top? Decimals, didn't we? Okay. Once you get this written in terms of one variable, do this for me. I'm going to write this down here. We're going to decimal it now. Okay. Here's what I'm going to do. Let me get decimals loaded up here quickly, kids. And you might want to do the same thing so you understand what we're looking for. All right. Do I have that bookmark, kids, or does it show up here anywhere? Oh, please. Wait. Oh, got it. Thanks. All right. In decimals, here's what I want you to do. Okay. We have that perimeter function that we're trying to minimize written all in terms of one variable x. So what you're going to do is just type that in. Okay. We have p equal to what?
2x plus 800 over x.
Okay, so type that in. Type in, ooh, where's my keyboard, guys? Does this say paused? What's this mean down here, kids? Help me. Oh, there it is. Oh, okay, I've got it. A little slow today. You guys okay with that? All right. What was that function again up there? 2x
Plus 800
plus 800 divided by what?
X.
All right, here's the deal. Ooh, Parson, nothing shows up on your graph. That's not good, is it? Something on show. Do what?
Zoom.
Start zooming out. Yep, let's do that. So I'm going to zoom out. So I want to go zoom, zoom, T-moomy zoomy. I guess I could put y equals in here. It doesn't like this for some reason.
Person, it's at like 100.
It's at 100.
It's what?
It's at 100.
Keep zooming out.
Keep zooming out.
Oh, keep zooming out. Okay. Ah, there it is. Do I want to deal with these negative numbers at all? Why not?
Isn't it because like an area can't be negative?
Yeah, we're looking for a perimeter. We can't measure negative distance. Okay? If we measured negative distance, we'd be time traveling. We'd all be young and look good. Well, you guys all look good, but I guess for me, time travel's for me, right? Yeah, okay. Where's the minimum point at, kids? Do you see a minimum point at? Gosh, look at what decimals even does here. Do you guys see this minimum point? Doesn't it make sense that point's a minimum right down here? Check this out. Click on that. Oh my gosh. That's where the minimum's going to occur for this perimeter. Now guys, we set this up in terms of x or terms of y here. Which variable did I use in my equation? So given that minimum point up there, what is the x value? 20. Okay, so what this is telling me is the following, kids. This is telling me, hey, where did I set my pen down at now? This is telling me from this that you'll get a minimum perimeter for fencing when x is what value?
20.
20. Okay. Now, let's go in and do this. So this means that from decimals, this x distance has to equal 20. Help me out, kids. If this is 20 and this is 20, is there any way to figure out your y value now? I know it said 80 on there, but here's the deal. When I set the equation up, did I ever have y in here as a function? No, we were minimizing with respect to what? So the only thing I can work with is x. So let's take a look here. Let's go back to some of our equations already here. We know x has to be what here, kids? 20. Take a look at this first equation. I highlighted it again. Could I plug 20 in for x now? It says 20 times what? Has to equal what? So to find y, I could say, well, from this right here, we know that 20 times y would have to equal 800. How could I use that now to find y? Divide by 20. Do that for me. 800 divided by 20. Guys, get 40. Okay? So this distance down here is 40. By the way, kids, what's 20 times 40?
800.
So that works. That goes along with what we're trying to accomplish, right? So the overall question comes back and says, by the way, what's the minimum amount of fencing you're going to use in this whole stuff? What are all three sides going to add up to, in other words? $20 plus 40 plus 20. Oh my gosh. Wasn't that point 20 comma 80 that we plotted? That point 80 really represented the amount of what? Amount of fencing that we would have used, right? Didn't we set an equation up here that said, oh, X will get us our minimum. Minimum for what? Perimeter. Well, when 80 kicked out, that 80 was your minimum perimeter, okay? So the dimensions would have been 20, 40, and 20, which all adds up to 80, okay? So the minimum distance here to enclose 800 square yards would be 80 yards of fencing. Now guys, tell me, is that an easy problem or is that pretty upper level? That's a pretty hard problem, okay? You know what the hard part about problems like this is? It's not so much doing the math, but you got to have a place to what? Yeah, you got to start somewhere, okay? You got to start somewhere. That's pretty tough stuff right there, okay? Questions about that example? How many think they could have gotten that on their own? I think every single one of you could have gotten started on it, I think. Okay? Questions at all so far? Going once, please? Let's roll last examples here, kids. Get you working on some things here this hour. Pretty sure you're tired of listening to me already. You guys normally all this quiet? Randy? First hour, I know, I'm sorry. You know what I'm going to do? I'm going to keep drinking some more of my coffee and keep getting more fired up. You should come in your second and third hour. Holy cow. We were bouncing off the walls yesterday. Fortunately, there's no holes in the ceiling right now. That's crazy. All right. A toy manufacturer paints a wooden cube with an edge of how long? 1.5 inches. Okay. It says a larger cube has linear dimensions that are twice the dimensions of the smaller cube. So here's a smaller cube that they painted. Question becomes this: does the larger cube require twice as much paint? So I have this cube. We paint it. Then there's a cube that's twice as long on each edge. Question becomes, do you use twice as much paint? How many think you use just twice as much paint if you double the dimensions? How many think you use not twice as much paint? How many think they're not sure? No problem. Okay. Talk me through this. This first cube, what are the dimensions of each cube, kids? 1.5 here for length, 1.5 for width, 1.5 for height. We're going to paint this. Okay, what's true about all faces of a cube? They're all the same. And in a cube, how many equal faces are there?
6.
6 of them. So let's talk about this right here. Let's talk about the smaller cube. Okay. One side's area would be, wouldn't that be 1.5 times 1.5, kids? Whoops, made a mistake there. All right, anybody know what 1.5 squared is? 2 point. I'll just write it here. It's 2.25 square units. And actually, we're going to use inches in this problem. Okay? The area of one side of that cube is 2.25 inches. However, in that cube, how many equal sides do you have?
6.
There's 6 of them, okay? So here's the deal. I'm going to times this by 6 now because there are 6 sides to this. Okay? You guys trust my math?
Yeah.
I'll just tell you this is 13.5. Okay. So how many square inches to paint on a smaller cube? How many square inches on a small cube? 13.5. Okay. Now some of you had your hands up in the air like, you won't use twice as much paint. Somebody fill me in why they're thinking that way. Anybody? Who had their hand up earlier? Gabriel, what do you think? Why do you think you're not going to use twice as much paint? Any idea?
Each side's four times the size.
How you come up with 4 times the size there, buddy?
Each thing is doubled, so that would be 9.
Okay. So you're telling me that by doubling the lengths, you're doubling a length and a width. So instead of like doubling one time, you're really like doubling twice. Let's check this out. Good. Guys, if I double the dimension rate here, 1.5 would double to what value? 3. Okay, so for this bigger cube that's twice as big, this would be 3, this would be 3, and this would be 3. So what's the area of one side going to be on the bigger cube?
9.
Going to be 9. Okay, so one side is 9. So what's that make 6 sides, kids? What's 9 times 6? 54. Okay, so for this one right here, you're using 54 square inches up to paint that completely. All right? Now, guys, they want to know if I'm doubling this right here. Okay? So what we're going to take a look at doing here is this. I want to look at a ratio here comparing the area of the bigger figure to the smaller figure. How much surface area in the bigger figure do we have to paint, kids? How much area in the bigger figure do we have to paint? 54 square inches. How much area in the smaller figure? Okay. So in this cube right here, somebody run 54 divided 13.5. 4. Okay. Did you get that? 4, Jaden? I think you multiplied instead of dividing. Yeah, no worries. Happens. I've already made 12 mistakes up here. You've only made 1 today. This 4 represents, if I double all the dimensions, it's like painting that smaller cube how many times to get the paint coverage for the bigger cube? How many times? 4. Okay. Just because I double the area doesn't mean you double the, or if I double the lengths doesn't mean that you double the amount of paint. You're actually using 4 times the amount of paint here. Okay. So you're going to be using 4 times the amount of paint. Okay. All right. Run through one more quick example here, and then I'm going to get you going on some things here today. Any questions about that? Rhett, every time I look up and see your sweatshirt, I think greatness. I tell you, you get an A for the day already. That's awesome. You made my day today. Love it. Okay, kids, last one. Right rectangular prism has the same base as the smaller what, kids? But it's just time, instead of, we're not doubling all dimensions, but we are gonna double the what? Yeah, we're gonna stretch the height out. It says, does the prism require twice as much paint as a smaller one? Let's check this out. So we already know for the small cube, from the previous problem, kids, how many square inches would it take to paint that? Okay, so I'm going to write this down. For the small cube, I know it takes 13.5 square inches to paint that. Okay, so let's look at what happens to the bigger one. So the big prism. So it said the base stays the same. So we've got a 1.5 here and a 1.5 here. But the height of 1.5 is going to double to what, kids? 3. Okay? That height is going to double to 3. All right? I'm going to do something here quickly. We need to find the surface area of that. How many square inches are we painting this time? So let me see if I can find... Okay. I found one. I like this. This is like 2 little cubes. If you cut this in half, you'd have a cube. This is kind of like that. So on this right here, we have 1.5 by 1.5 for the bottom, don't we? Okay. Is it okay if I write on this? 1.15 times 1.5 is 2.25. How many sides of 2.25 am I going to have, though? 2 of them, a top and a bottom. Okay. So for this big prism, I'm going to say, you know what? Both the top and the bottom. Top is 2.25. Bottom is 2.25. Okay, let's talk about one of these sides. One of these sides would have an area of what times what, kids?
3 times 2.5.
3 times
1.5.
1.5. So one side would be 3 times 1.5. What is 3 times 1.5?
4.5.
Okay. So each side is 4.5. That comes from, again, this 1.5 distance down here times this height is now what, kids? Okay, so 1.5 times 3 gets us that area of 4.5. But how many sides of 4.5 do we have here? 4 of them, right? So for the sides, we have 4 of these. So I'm going to take 4.5 times 4. That equals 18. So the 4 sides are 18. The top and the bottom are how much, kids?
Each.
2.25, 2.2. Quick question. How am I going to find the total surface area for the big prism? Well, you got top and the bottom, 2.25 and 2.25 added. That's 4.5. And then 4.5 plus how much more, kids? 18. 4.5 and 18. 22.5 square inches. So if I want to know if I am doubling the amount of paint just by changing the height, and I think I have that right. We have to look at a ratio, don't we? So let's look at this ratio of big to small. For the big prism, how much area?
2.25.
So 22.5, right? Okay. How about for the little cube? What's the area there? What was the area of the little cube, kids? Okay. Let's see. If I take 22.5, the ratio I get is 1.6 repeating. So am I using twice as much paint or not? No, you're only using 1.6 times that, okay? So just because you're doubling dimensions doesn't necessarily mean you're gonna double the amount of paint you use, okay? That'll be good for you when you guys buy a house and start remodeling to know, right? I can see every single one of you sitting down saying, okay, how much paint do I need to buy? Or you could go to Lowe's or Home Depot and they'll just tell you. What questions do you have? I'll apologize, I'm a little fired up. I get a little geeked out about this stuff, so I hope you're okay with that. Any questions for me today, kids? All right, let me minimize this. I want to get you going on some things. I do have a short, quick quiz.